Module 4, Lecture B, Pythonic Searching. By the end of this lecture, you will be able to use Python's built-in search capabilities effectively for common tasks. Apply the bisect module to maintain sorted sequences efficiently. And relate high-level Python search constructs to their underlying algorithmic behavior. Python built-in search. Membership testing basics. In Python, searching usually means checking whether a value is a member of a collection, such as seeing if a student ID is on a list or a word is in a set of banned terms. These membership checks are easy to write, but their speed depends on the type of collection you choose. Looking through a list, a set, or a dictionary can have very different performance, especially as the amount of data grows. Understanding these differences is essential for writing programs that stay both correct and efficient at larger scales. In programming, checking whether a value is already present in a collection is important for tasks like avoiding duplicate emails in survey data, or confirming that a value belongs to a valid category. This kind of membership testing also appears in web applications. For example, when verifying that a feature flag is recognized before turning it on. The choice of data structure has a big impact on how fast these checks are. Lists are slower because they must scan through each element, especially as the data grows. In contrast, sets and dictionaries support much faster, almost constant-time membership tests, making them better suited for quick lookups and validation. Membership testing in Python is not only about speed, but also about clearly expressing what your code is doing. When you check whether a value belongs to a group, such as a username in a blocked list or a sensor reading in a set of fault codes, you are encoding rules and domain knowledge directly into your program. Choosing appropriate data structures, like sets for unordered groups and lists for ordered ones, helps align your code with these rules. This leads to clearer, more expressive programs and ensures that your searches are both correct and efficient. Python code membership testing basics. This section focuses on how to test whether something is a member of different collection types, such as lists, sets, and dictionaries. It explains that membership testing works differently depending on the collection, so the meaning of asking whether an item is contained can change. By comparing simple, everyday-style examples, you see how membership in a list, a set, or a dictionary can answer slightly different questions, even though the basic idea of checking for presence stays the same. This line is telling you that you do not need to run any pip install commands because the script only uses features that come built into Python. In other words, it relies entirely on Python's standard tools and does not depend on any extra libraries. Everything the script needs is already available by default when you have Python installed. We use different data structures depending on what we need to do. A list can store students in the order they are waiting in line, which is useful when the sequence matters, like in a queue. A set can store blocked usernames because it lets us quickly check whether a user is not allowed access. A dictionary can map product codes to their prices in dollars, so we can efficiently look up a price using a unique product identifier. We start by setting a variable to the name we want to find, in this case, Carol, and then we print whether that name appears in the waiting list. The membership check goes through each item in the list until it either finds the name or reaches the end. This process works correctly, but becomes slower as the list gets longer. It is generally less efficient than doing the same kind of check with sets or dictionaries. We set a login name to a specific username and then check whether that username appears in a set of blocked users. We use a print statement to show the result of this membership test. Because sets are designed for fast lookups, this check is efficient. The printed message tells us if that username is blocked based on whether it is found in the set. We choose a product code, such as B200, and use it to check whether that code exists in a dictionary that stores product prices. The dictionary links each product code to its price, so we can quickly see if the code is present. We then print a message indicating whether the product code was found. This works efficiently because dictionaries are designed for fast lookups based on their keys. Imagine you have a price value, such as 9.99, and a dictionary that maps product codes to their prices. If you check whether that price is in the dictionary, the check is performed on the keys, not on the prices stored as values. This means the membership test looks for a matching product code, not a matching price. This behavior is a common source of confusion. So it is important to remember that dictionary membership checks always apply to keys by default. This content explains that the code is used to highlight how different data structures perform when checking if an item is present. It emphasizes that sets and dictionaries allow very fast membership tests, while lists are slower, especially when they contain many elements. The message is stored in a string and printed to the console to reinforce the idea. Overall, it shows that choosing the right data structure can greatly improve performance for membership checking operations. This script compares how membership checks work in different Python collections. It tests whether a name is in a list, a username is in a set, and a product code is in a dictionary. Lists may be slower for large collections because they scan each element, while sets provide fast checks, making them efficient for tasks like verifying blocked users. In dictionaries, membership testing looks only at keys, so a known product code is found, but a price value is not. Overall, sets and dictionaries are preferred for fast membership tests in large datasets, while lists are less efficient for this purpose. Index search and errors. Index-based searching in Python is used to find where a value appears in a sequence, such as a list, tuple, or string. It returns an integer that gives the position of the first matching item, starting from 0. This position can then be used to retrieve or modify elements. For example, to match a product name with its price. Understanding how this search works and what it assumes about the data helps you use Python search features effectively. When you search by index in Python, you must plan for the case where the value is not found. Instead of returning a special value, Python raises an error to signal that the search failed. This forces you to deal with the missing value rather than using an invalid index. In practice, you should either check that the value exists before searching or handle the error when it occurs, which is especially important in tasks like data cleaning to prevent scripts from crashing when expected patterns are missing. When working with index searches, build habits that assume a search might fail as well as succeed. Design your logic to handle both finding a value and dealing with its absence so your program stays robust. For instance, a recommendation system might fall back to a default strategy if a user is not found, and a financial tool might log missing account data as an anomaly while continuing other analyses. By anticipating these cases, you turn index searches into reliable decision points that support solid software engineering practices. Python code, index, search, and errors. This section shows how to search for values in lists and strings using index positions, and illustrates what happens when the value you search for is not present. You will see simple examples where the search succeeds and returns a position, and cases where it fails and triggers an error. It also compares directly calling an index operation, which can raise an error when the value is missing, with safer membership checks that first test whether the value exists before trying to access its position. This line indicates where you would install any libraries needed for the script to run. It implies using a package manager to make sure all required dependencies are available, even though no specific library is named. Including such a step is a common way to prepare the environment before executing a Python script. We begin by creating a shopping list that contains 4 items: milk, bread, eggs, and butter. This list will later be used to demonstrate how searching works. In Python, a list is an ordered collection, which means each item has a specific position. Because of this ordering, we can access items by their index, making it useful for showing index-based search operations. We use the index method on the shopping list to find where the item milk is located. This method searches through the list and returns the position of milk, starting the count at 0. It is a straightforward way to get the exact position of an item when we already know it is in the list. This line displays the position of milk in the shopping list using zero-based indexing, where counting starts at 0. The position was obtained with the index method, which returns the first place where the specified item appears. Seeing this output confirms that milk is in the list and shows exactly where it is located. We begin by assigning the word cheese to a variable so we can easily work with it in our program. This lets us check whether cheese appears in a shopping list and reuse that same value wherever needed. Using a variable in this way makes membership checks and finding its position in the list simpler and more consistent. We first check whether the item cheese is in the shopping list using a membership test, which safely tells us if it exists before we look for its position. If cheese is present, we then call the index method to find and announce its position in the list. This approach prevents errors because we only search for the index after confirming the item is there. If cheese is not found, we simply report that it is missing, avoiding any index-related problems. This example shows how to handle errors when searching for an item in a list. The code tries to find the position of the word cheese using the list's index method. But because cheese is not in the list, this raises a value error. To prevent the program from crashing, the operation is placed inside a try block. When the error occurs, the except block catches the value error and prints a message explaining that the direct index call failed. This demonstrates how a try-except structure can safely manage exceptions when an expected item is not found. We begin with a simple text value that says "Hello World." which we will use to show how to find where a character appears inside a piece of text. By setting up this example, we can focus on learning how to locate specific characters. This will let us explore how indexing works to identify the position of each character within the text. This part of the code finds the position of a specific character in a string. It uses a method that searches the text, which in this case is the phrase "Hello World" for the character W. The method returns the position of the first time W appears, counting from 0. This tells us exactly where that character is located within the string. This code finds and prints the position of the letter W in the phrase "Hello World." It uses zero-based indexing, which means counting starts at 0 instead of 1. This is the standard way Python refers to positions in strings and lists. This script shows how to safely search for items in lists and strings in Python using the index method. It first finds the position of an item that exists in a shopping list, then checks whether another item is in the list before trying to get its index, avoiding an error when the item is missing. It also demonstrates what happens if you call the index method directly on an item that is not present, which raises a value error that can be caught and handled. Finally, it applies the same idea to a string by finding the position of a character, emphasizing the difference between safe membership checks and direct index calls that may raise exceptions. Predicates with any and all. In Python, you can efficiently check conditions across a whole collection using the built-in tools called any and all. These let you see whether at least one element or every element meets a condition without writing manual loops or tracking flags yourself. Python handles the iteration and stops early when it already knows the answer. For example, you might test whether any student missed more than 3 assignments, or whether all sensor readings stay within a safe range. Using these predicates leads to concise, idiomatic code that is easier to read and maintain. Predicates like any and all are used with a condition that is checked for each element in a collection. For example, you might see if any email subject contains a keyword, if all configuration entries are filled in, if any transaction exceeds a fraud limit, or if all dataset values are valid. These checks return a single true or false value that can drive actions such as raising an alert or skipping a step. They also stop evaluating as soon as the outcome is determined, which makes them more efficient than scanning every element, especially when you only need to detect the first failure. These predicates work like specialized searches that scan through data one item at a time until they can answer your question. In the worst case, they examine every element, much like a full loop. However, they use short-circuit evaluation, which means they stop as soon as the result is known, such as when they find the first invalid input in a form. Understanding them this way helps you arrange your conditions and data so they can exit early and run more efficiently. Python code, predicates with any and all. We will explore how to use quick checks on collections with 2 common tools. First, we will show how to use a function that returns true if any element in a collection meets a condition, which is useful for fast, simple checks. Then, we will demonstrate a function that returns true only if every element satisfies a condition, which is helpful for full validation. Along the way, we will use beginner-friendly examples to highlight how these checks stop early as soon as the result is known, a behavior called short-circuiting. This comment explains that the script only uses Python's built-in standard library, so no extra packages need to be installed. This means the code has no external dependencies. As a result, it is easier to run in different environments and more accessible to users, since they can execute it without additional setup. We define a list of numbers that represent daily temperatures measured in degrees Fahrenheit. These values are typical readings over a week, ranging from the upper 60s to the low 80s. This list will later help us check conditions, such as whether any day reached a particularly high temperature. We use a list of homework completion flags to track whether each student has finished their assignment. Each position in the list corresponds to a student, and the value is either true if they completed the homework or false if they did not. This list will later allow us to quickly check if every student has turned in their work. We can use the any function to quickly check whether there is at least one day with a temperature above 80 degrees Fahrenheit. It goes through the list of daily temperatures and tests each value against this threshold. As soon as it finds a temperature that is higher than 80, it returns true and stops checking the rest. This short-circuit behavior makes it efficient for deciding if any day was uncomfortably hot without examining every single entry. The all function is used to quickly check whether every student has completed their homework. It takes a list of true or false values, where each value shows if a student has finished their assignments. If every value in the list is true, the function returns true, meaning all students are done. If even one value is false, it returns false, indicating at least one student has not completed the homework. This makes it an efficient way to confirm that a condition holds for an entire group. This line prints a message to the console that tells you whether any day in the temperature list went over 80 degrees Fahrenheit. It uses a stored true or false value produced by the any function, which checks all the temperatures. If at least one temperature is above 80, it prints true. If none are, it prints false. This gives a quick summary of whether there was a particularly hot day. The code prints a message that reports whether all students have finished their homework. It relies on a previous check that used a function to test if every homework completion flag in a list is true. That result is stored in a variable and then printed along with the message stating that all students completed their homework. This gives a clear, single summary of the homework status for the entire class. We define a function called isVaryHot that takes a temperature as input and prints which temperature it is checking, so we can follow the flow when the function runs. The function then returns true if the temperature is 90 degrees or higher, and false otherwise. This simple setup is mainly used to show how the any function can stop checking early, as soon as it encounters a temperature that meets this very hot condition. We use a function that checks whether any day in a list of Fahrenheit temperatures reaches at least 90 degrees. A generator expression goes through each temperature and calls another function that reports which value is being checked, and returns true if it is 90 or higher. The any function evaluates these results And because it stops as soon as it finds a temperature that meets the condition, it avoids unnecessary checks. This short-circuit behavior makes the overall process more efficient. The code prints whether any day in the list of temperatures reached at least 90 degrees Fahrenheit. It relies on an earlier use of the any function with a generator that checked each temperature against this threshold. As soon as one temperature met or exceeded 90 degrees, the any function returned true and stopped checking the rest. The printed result clearly indicates whether there was at least one very hot day in the dataset. This script shows how the any and all functions evaluate conditions across a collection. It first checks whether any temperature in a list is above 80 degrees, which is true because at least one value is that high. It then checks whether all students finished their homework, which is false because one student did not. Finally, it demonstrates short-circuit behavior by checking whether any temperature reaches 90 degrees. Printing each value as it is tested and stopping as soon as a match is found. This illustrates that any can end early once a true condition appears, while all only succeeds if every condition is true. Python bisect essentials. Bisect left versus right. When working with sorted data in Python, it is important to know not only whether a value is present, but also where it should go to keep the order correct. You can choose to insert a new value on the left or on the right of existing equal values. Left insertion places the new value before the first matching element, while right insertion places it after the last matching element. This choice controls how duplicates are arranged and where new values appear relative to those already in the sorted data. When managing a sorted list of timestamps for customer orders, there are two ways to insert new orders that share the same time. A left-style insertion places new orders before existing ones with that timestamp, so the earliest original order gradually moves to the right. A right-style insertion does the opposite, placing new orders after existing ones and keeping the earliest order at the left. Both approaches keep the list in chronological order, but they handle ties differently, which can change how you interpret the sequence of events or priorities. When working with sorted lists in Python, choosing between left and right insertion affects how you interpret search results. The left version returns the position of the first occurrence of a value, while the right version returns the position just after the last occurrence, creating a half-open interval that covers all matching elements. These boundaries let you efficiently count how many times a value appears, extract all items in a given range, or check whether a value is present, all using the speed of binary search. Understanding when to use each variant helps you keep your logic consistent and efficient as your data grows. Python code. Bisect left versus right. Use simple sorted numbers to demonstrate how the bisect left and bisect right operations behave. Show that when you insert a value that already exists, the left version places it before the existing equal values, while the right version places it after them. Explain how these different insertion positions help you count how many duplicates are in the list and locate where those duplicate values begin and end in the sorted order. In this part of the code, we do not need any pip install commands because everything we use comes from Python's standard library. All required functionality, including tools like the bisect module, is already built into Python. This makes the code easier to run in different environments, since there are no extra dependencies to manage. As a result, the program is more portable and simpler to set up. We use the bisect module to work efficiently with sorted lists using a binary search-style approach. The bisect left and bisect right functions find where a new element should go in a sorted list to keep the order, either before or after any equal values. The insort left and insort right functions go a step further by actually inserting the element into the list at the correct position. Together, these tools make it easy to maintain sorted data, even when there are duplicate values. We begin with a sorted list of customer order times in seconds: 10, 20, 20, 20, 30, and 40. This ordered sequence gives us a simple example to study how inserting new values works when the list already contains duplicates. By focusing on the repeated value of 20, we can see how different insertion strategies determine where a new value is placed among existing equal entries in a sorted list. We begin by printing the original list of timestamps so we can see its initial sorted order before making any changes. This gives us a clear baseline for comparison as we apply different insertion methods. By referring back to the starting state, we can better understand how each insertion strategy alters the list over time. In this example, we focus on the timestamp value 20, which already appears in the sorted list. Choosing a value that is duplicated lets us see how the bisect functions behave when the same number occurs more than once. By examining this repeated value, we can compare the insertion positions returned by the left bisect and right bisect operations. This comparison is key to understanding how these functions handle duplicates in a sorted sequence. The bisect left function from the bisect module is used to find where a value should be inserted in a sorted list to keep the order correct. It returns the index where the new value would go, placing it before any existing entries with the same value. In this example, we use it on a list of timestamps with the value 20 to find the position just before the first 20 in the list. To find the correct insertion position in a sorted list, we use the bisect right function from the bisect module. This function returns the index where a given value should be inserted so that it appears after any existing copies of that value. In this example, we apply it to the list of timestamps with the value 20. The result is the index just after the last 20 in the list, which is stored in a variable. This tells us where a new 20 would go if we wanted it to come after all current 20s. We print the left and right insertion indices to show where the value 20 would go in a sorted list. The left index marks the position just before the first 20. And the right index marks the position just after the last 20. Comparing these positions illustrates how the bisect left and bisect right style functions choose insertion points when there are duplicate values in the list. We begin by making a separate copy of the list of timestamps so the original data is not changed. This copy is stored in a new variable. We then use the insort left function from the bisect module to insert a new timestamp into the copied list, while keeping it sorted. This function places the new value before the first existing value that is equal to it. This method is useful when you need to maintain sorted order and want any duplicates to appear at the earliest possible position in the list. We begin by making a copy of the list of timestamps so the original data stays unchanged, and we use this copy to insert a new value. To place the new timestamp correctly, we apply the right-side insertion method from the bisect module, which inserts the value after the last existing occurrence of that same timestamp. This keeps the list in order while ensuring that any duplicates appear at the end of their group. Overall, this approach preserves both the original data and the sorted structure of the list. After inserting a value with the left insertion strategy, we print the list to show that the new timestamp appears before the first existing entry with the same value. We then insert the same value using the right insertion strategy and print the list again, this time seeing the new timestamp placed after the last matching entry. Comparing these two outputs highlights how left and right insertion strategies handle the placement of duplicate values differently. To find how many timestamps in the list are equal to 20, we use the left and right insertion positions for that value. The left insertion index marks where the first 20 would be placed, and the right insertion index marks where the last 20 would go. Subtracting the left index from the right index gives the total number of times 20 appears in the list. This difference directly represents the count of that value's occurrences. We find how many times the value 20 appears in the list by subtracting its leftmost index from its rightmost index. This difference gives the count of duplicate timestamps. We then show the range between these indices to indicate where the duplicates occur in the sorted list. Together, this reveals how equal values are distributed within the timestamps. This script shows how Python's bisect tools find insertion points in a sorted list when there are duplicate values. Using the left variant, it finds the position just before the first occurrence of a chosen value, and using the right variant, it finds the position just after the last occurrence. It then inserts another copy of that value using both strategies to show how the list changes when the new item is placed at the leftmost or rightmost position among the duplicates. Finally, it subtracts the left index from the right index to count how many times the value appears, demonstrating an efficient way to locate and count duplicates in sorted data. Managing sorted lists. The bisect module helps you keep a list sorted as you add new elements, without having to sort the entire list each time. It quickly finds the correct position for each new item so the list stays in order. This is especially useful when data arrives gradually, such as timestamped logs or ranked items in a recommendation system. By inserting each element in the right place, you avoid expensive full sorts and enable fast, reliable operations on ordered data. The bisect module helps you keep a list always sorted by separating the search for the correct position from the actual insertion. It quickly finds where a new element should go based on the current order, then inserts it there and shifts other items as needed. This is useful for maintaining ordered data, such as driver ratings, patient severity scores, or delivery times. By keeping the list sorted after each insertion, it makes operations like finding medians or identifying values above a threshold more efficient, without having to sort the entire list again. When using the bisect approach to keep a list sorted, remember that Python lists are stored in one continuous block of memory. So inserting items in the middle can be slow because many elements must be shifted. Bisect itself is efficient at finding where a new item should go, but the real cost depends on how often and where you insert. For large lists with frequent insertions, a different data structure, such as a balanced tree, may be more suitable. For moderate list sizes or infrequent insertions, bisect is usually a practical and efficient way to maintain order using binary search. Python code: managing sorted lists. This section explains how to keep a list sorted by using bisect-based insert operations. Instead of appending new values and then sorting the entire list again, bisect finds the correct position for each new value as it is added. This approach maintains the sorted order automatically and avoids the cost of repeatedly resorting the whole list. The goal is to compare this naive append and sort method with the more efficient bisect-based insertion strategy. This note explains that you do not need to run pip install for modules that are part of Python's standard library. Built-in modules such as the bisect module are already included with Python. Because they come pre-packaged, you can use them right away without any extra installation steps. This simplifies your setup and helps you avoid unnecessary commands when working with standard library features. The code starts by importing the bisect module, which helps keep a list sorted as new elements are added. Instead of sorting the entire list after each insertion, bisect uses binary search to quickly find the correct position for a new item. This keeps the list in order efficiently and is especially useful when you need to insert many elements into a sorted list. We begin with a list of delivery times in minutes that is already sorted in ascending order, with smaller times, like 18 and 22, coming before larger ones, like 45 and 60. The key idea is that starting with a sorted list makes it easier to keep the data organized as new delivery times are added during the day. Instead of sorting the entire list again each time, we can insert each new time into its correct position. This approach maintains the sorted order efficiently while the list grows. We begin by creating a list of delivery times called the naive version, which starts with the same values as the sorted list, but is left unsorted on purpose. New delivery times are simply added to the end of this list without maintaining any order. This setup represents a straightforward but inefficient approach. It allows us to later compare how much more efficient a method that keeps the list ordered can be, compared with this simple append-only strategy. We have a list of new delivery times arriving during the day with values of 25, 50, and 35. These values represent additional delivery times that need to be added to an existing list that is already sorted. By inserting these new times into the sorted list as they come in, we can keep the overall list ordered efficiently while new data is continuously added. We process each new delivery time by finding where it belongs in the existing sorted list and inserting it at that position. To do this efficiently, we use a binary search approach provided by the bisect module, which quickly locates the correct insertion point. This keeps the list sorted at all times without having to sort the entire list again after each insertion. As a result, we maintain order with minimal extra work. To insert a new delivery time into an already sorted list, we can use the bisect module's bisect right function. This function quickly finds the correct position for the new time so the list stays in order. By doing this, we avoid resorting the entire list after each insertion. This approach is especially useful and efficient when working with large datasets. The code adds a new delivery time into a list that is already sorted by finding the correct index with a bisect operation and then using the list's insert method. This places the new time directly into its proper position. As a result, the list stays sorted without having to sort the entire list again, which makes the process more efficient. In a simple but inefficient approach to handling new delivery times, we take each new time, add it to the end of the existing list, and then sort the entire list again to restore the correct order. This means that for every single insertion, we repeat a full sort of all delivery times. While this method is easy to implement, it becomes slow and wasteful for large lists because the whole list is repeatedly resorted instead of placing each new time directly into its proper position. The code simply adds each new delivery time to the end of the list without placing it in the correct sorted position. This makes the logic easy to write but inefficient for keeping the list ordered. After every insertion, the entire list must be sorted again to restore the correct order, which is not an optimal approach. Sorting the entire list again after each insertion is inefficient, especially for large lists. This method is more resource-intensive because it repeatedly rearranges all elements. A better approach is to insert each new element directly into its correct position. This avoids unnecessary work and makes the overall process more efficient. We now display the list that was built using the bisect method. Each new delivery time was inserted directly into its correct position, so the list stayed in order as values were added. The printed output confirms that the delivery times are sorted throughout the process. This shows that we can maintain a sorted list without having to sort the entire list again after each insertion. This code prints a list of delivery times that has been kept in order using a naive method. Each new time is simply added to the end of the list, and then the entire list is sorted again. While this does produce a correctly ordered list, it is inefficient for larger datasets because it repeats a full sort after every insertion. The example highlights this inefficiency and contrasts it with using a bisect-based approach, which maintains sorted order more efficiently as new items are added. This script compares two ways to keep a list of delivery times sorted. One method uses the bisect module to find the correct position for each new time and insert it directly into the existing sorted list, avoiding a full resort. The other method simply adds each new time to the end of the list and then sorts the entire list again. Both approaches produce the same final sorted list, but the bisect method does it with fewer operations and is more efficient, especially as the list grows larger. Inside binary search, the bisect module is based on the idea of binary search on a sorted list. Instead of checking each element in order, it repeatedly compares the target value to the middle element of the current range. If the target is smaller, it continues searching in the left half. If it is larger, it searches in the right half. This process continues until it finds the correct position or determines the value is not present. Because the list is sorted, the algorithm can quickly discard large portions of data, making it efficient even for large lists. The bisect module in Python automatically performs a binary search to find where a new value should be inserted in a sorted list. It repeatedly checks the middle of the current range and narrows the search based on comparisons until it finds the correct position. Because each step cuts the search space in half, this method is very efficient, especially for large datasets such as transaction logs or sensor readings. Using bisect keeps the list ordered and allows quick searches without manually moving elements around. The bisect module uses binary search on a sorted list, so it can quickly find where a new element should be placed by checking only a few positions. However, actually inserting the element can be slower because many existing items may need to be shifted. This trade-off makes bisect well-suited for situations with many searches but relatively few insertions, such as maintaining top scores in a game or handling a small scheduling system, where it keeps the code efficient and simple. Python code inside binary search. This lesson explains how binary search works inside bisect operations on a sorted list of numbers. It shows how the algorithm repeatedly checks the midpoint of the current range, then narrows the range by moving either the low or high boundary based on that comparison. By walking through these midpoint checks and range updates, you can see exactly how the search zone shrinks step by step. Finally, it connects these manual binary search steps to the insertion index that the Python bisect tool computes for placing a new value in order. This line is simply a comment noting that you do not need any pip install commands for this script. It explains that the program uses only Python's standard library, which is already included with Python. As a result, all required features are built in, and there is no need to install extra packages. We begin by importing the bisect module, which helps keep a list in sorted order without repeatedly sorting it. In this script, bisect is used to find where a new value should be inserted in a sorted list. We then compare this built-in approach with a manual binary search. This comparison shows that both the manual method and the automated bisect tool can achieve the same goal of efficiently locating insertion points in a sorted list. We begin with a list of mile positions along a highway that is sorted in ascending order. This sorted list is essential because binary search depends on ordered data to quickly narrow down where to look. With these predefined mile markers, we can efficiently determine where a new mile marker or target position should be inserted so that the list remains in the correct order. We define a target mile marker of 85 to represent where a new highway sign might be placed. This target value is used in a binary search to find the correct position for the sign within a sorted list of existing mile markers. By comparing the target to the existing positions, the search determines exactly where the new sign should be inserted. To begin a manual binary search, we first set the low boundary to 0, marking the start of the list of mile positions, and the high boundary to the length of the list, marking its end. These two boundaries define the full range of indices we will search. With this setup, we can systematically narrow down where the target mile marker should be inserted within the list. We begin by printing a short header that explains the manual binary search steps we are about to follow. This introduction prepares the listener for how the search will work and what to expect. It also makes clear that our goal is to find the target mile marker, which is 85. Overall, the header provides context, so the upcoming search operations are easier to understand. In this binary search loop, the condition that the low index must be strictly less than the high index ensures there is still a non-empty range to search. As long as this condition holds, there are elements between the current bounds that might contain or border the target value. The loop uses this condition to keep narrowing the search range. It continues until the remaining range is small enough to identify the correct insertion point for the target. To find the midpoint index between the current low and high bounds, the algorithm takes their average using integer division by 2. This calculation gives the index in the middle of the current search range. Identifying this middle position is essential in a binary search because it determines where to compare the target value and how to narrow the search space for the next step. The code looks up the mile position stored at the current midpoint index in the list. This value is then compared with the target mile marker to decide how to adjust the search. If the target is smaller, the search range moves to the left. If it is larger, the range moves to the right. By repeatedly using this midpoint value, the binary search quickly narrows down where the target mile should be inserted. This line of output shows the current range of indices being checked in the binary search, along with the midpoint index and the value stored there. It lets you see how the search interval changes at each step. By watching these values, you can better understand how the algorithm narrows down the possible location of the target and how each decision is made during the search. In this step of the binary search, the code checks whether the target mile is less than or equal to the value at the current midpoint in the list. If it is, the algorithm assumes the target must lie somewhere in the left half of the current range. To reflect this, it moves the high bound down to the midpoint index. This narrows the search to the left side and allows the binary search to continue refining where the target might be. In this step of the algorithm, we update the upper bound of the search range. If the target mile marker is less than or equal to the value at the midpoint, we move the high bound to that midpoint index. This narrows the search to the left half of the current range. By repeatedly doing this, the algorithm efficiently converges on the correct insertion index using binary search principles. Here, the code handles the case where the target mile marker is larger than the value at the current midpoint, which means the target must lie in the right half of the current range. To focus the search there, it moves the lower bound to just after the midpoint. This change narrows the search to the upper portion of the range and lets the loop continue refining the possible positions. By repeating this process, the algorithm eventually finds the correct place to insert the target. Here we are updating the lower boundary of the search range in a binary search. If the target mile marker is greater than the value at the current midpoint, the target must lie in the right half of the range. To reflect this, we move the low boundary to one position after the midpoint. This discards the left half, including the midpoint, and continues the search only in the upper half, making the process more efficient. When the loop finishes, the low and high indices have converged to the same position in the list. This shared position is exactly where the target mile marker would need to be inserted to keep the list in order. We store this position in a variable called the manual index, which represents the final result of our manual binary search. We use the bisect module's left side search function to find where a target mile should be inserted in a sorted list of mile positions. This function runs a binary search to locate the correct insertion point while keeping the list in order. It returns the index where the target mile belongs so the list stays sorted. This method is efficient and takes advantage of Python's built-in binary search capabilities to quickly find the right position. The code prints two insertion indices so you can compare them. One index comes from a custom binary search, and the other comes from the built-in binary search in the bisect module. Both are used to find where a target mile marker should be inserted in a sorted list of mile positions. By comparing these two indices, you can confirm that the manual method and the bisect function produce the same result. This script shows how to find where to insert a new mile marker in a sorted list using both a manual binary search and Python's bisect tool. The manual method repeatedly compares the target mile, in this case 85, with the middle element of the current range, and then narrows the range until it finds the correct insertion index. The script then uses the bisect left function to compute the same index automatically. By comparing the two results, it demonstrates that both approaches agree and illustrates how binary search efficiently locates the insertion point in a sorted list. Pythonic search idioms. Looping versus in operator. When you need to search in a collection in Python, you can either write a loop yourself or use the membership operator, which reads like natural language. This operator checks whether a value appears in a list, set, dictionary, or string without you having to code the search manually. Internally, it still examines elements one by one for lists and tuples, but uses faster hash-based lookups for sets and dictionaries. Its main benefit is that it lets you search clearly and concisely, while Python automatically chooses an efficient search method based on the data structure. When checking whether a value appears in a collection, both performance and clarity matter. Using a loop to scan through items does a linear search, so the time it takes grows as the collection gets larger. Converting the data to a set and using the membership operator instead relies on hashing, which makes the check effectively constant time, regardless of size. Even though both approaches answer the same yes or no question, the choice of data structure and operator can make the search either slow or fast. This shows how a small change in syntax can lead to a large difference in algorithm efficiency. The membership operator in Python is not magical. It is just a compact way to express a search that depends on the type of container. Writing the search as an explicit loop reveals details like checking each element and using early exits, while the membership operator hides these details and can make performance issues less obvious. A good programmer understands that lists and tuples usually mean a linear scan. Sets and dictionaries use hash-based lookups. And strings involve scanning characters. Keeping this mental model lets you enjoy Python's readable style while still understanding the time and space costs of your code. Python code, looping versus in operator. We want to compare two ways of checking if a value is in a collection, using a manual loop that inspects each element one by one, and using the built-in membership operator that directly answers whether the value is present. Both methods solve the same membership question, but they do it differently. A looping search walks through the list step by step, which can become slow when the list is very large. In contrast, using the membership operator with a set container is typically much faster for large collections, because sets are designed to answer membership questions efficiently. This contrast helps build intuition about why the choice of data structure and search method matters for performance. This line is simply a placeholder comment indicating that if needed, additional Python packages could be installed using a package manager. In this particular script, only the standard Python libraries are used, so no installation command is actually run. The comment mainly serves as a reminder for future updates in case the code is expanded to rely on external dependencies. We begin with a list of customer identifiers, where each identifier is a unique string representing one customer. This list serves as a simple dataset for exploring how to search for a specific identifier within a collection. Using it, we can compare basic approaches like checking each element one by one with more advanced membership operations. The goal is to examine how these different search techniques perform in terms of efficiency. We choose a specific customer identifier, cust150, that we already know is in our list. This guarantees that our later search operations will successfully find it. By doing this, we can focus on comparing how efficiently different search methods locate a known item, rather than worrying about whether the identifier exists in the data. We begin by setting a counter for comparisons to 0, so we can track how many checks we make while searching through the list of customer identifiers. Starting at 0 ensures that every comparison made during the search is counted accurately. This helps us measure the efficiency of our manual search process. We begin by marking that the target has not been found yet. Then we loop through each customer identifier in the list, increasing a counter each time to record how many comparisons we make. For each identifier, we check whether it matches the target. If we find a match, we update the flag to show the target was found and immediately exit the loop to avoid any further unnecessary checks. We use the membership operator, spoken as the word in, to check whether a target identifier appears in a list of customer identifiers. To estimate how many comparisons this might take, we look at the length of the list. In the worst case, the operator may need to examine every element one by one. That means the number of comparisons can be as large as the total number of items in the list. We convert the list of customer identifiers into a set so we can check membership more efficiently. A set uses hash-based lookup, which is typically much faster than scanning through a list. This means checking whether an item is present in a set usually takes constant time on average, instead of the slower, linear time needed for a list. We check whether the target identifier appears in the set of customer identifiers using a membership test. Because sets use hash-based lookup, This check is usually faster than scanning through a list, especially when working with large amounts of data. The outcome of this test is then stored in a variable that records whether the target identifier was found. We are estimating how many checks are needed when using a set to test whether an item is present. Conceptually, we treat this as just one check to highlight how efficient sets are. This reflects the idea that hash-based lookups in a set usually find what they need very quickly. In contrast, checking membership in a list may require examining many elements one by one, making it less efficient. We display the results of the loop search to show whether the target identifier was found and how many comparisons were needed. The output includes a true or false value, indicating if the search succeeded, along with the count of elements checked. By looking at these two pieces of information, we can see how efficiently the loop search method located the target in the data. This line of code prints the result of using the membership operator on a list of customers, checking whether a specific identifier is present. It outputs a short message followed by either true or false, depending on whether the identifier is found. It then prints how many comparisons were made, which equals the length of the list. Because the membership operator conceptually scans through each element one by one. We use the membership operator on a set to check whether a specific customer identifier is present, and we store the result as a simple true or false value indicating if it was found. Along with this, we track an estimated number of checks, which is effectively constant because set lookups use efficient hash-based access. This highlights that using a set for membership testing is much faster and more scalable than using a list, especially as the number of customer identifiers grows. This script compares 3 ways to check if a customer ID is in a collection. First, it uses a manual loop, where the number of comparisons depends on how far into the list the target appears. Then, it uses the membership operator on the list, which conceptually may check every element, so the number of comparisons grows with the list's length. Finally, it converts the list to a set and uses the membership operator again, which relies on hash-based lookup and is effectively constant time. The key conclusion is that while all methods find the target, using a set for membership checks is much more efficient for large datasets. Generator-powered search. In Python, generator-based search lets you scan through data one item at a time, checking each item against a condition only when needed. The search stops as soon as an item satisfies the condition, so it does not process the remaining elements. This works like a short-circuiting linear search, where items are checked in order and the process ends on the first match or when everything has been checked. By separating how candidate items are produced from how they are used, generators reduce unnecessary work and memory use while keeping the search logic clear and readable. Imagine scanning a long list of customer records to find the first overdue account with no interaction in over a year. A generator works like a small factory that processes one record at a time, checks the conditions, and either returns that record or moves on to the next. When combined with a tool that stops as soon as it finds a match, this behaves like a linear search that exits early. The time cost depends on how many records you examine, But memory use stays low because you only hold the current record and minimal tracking information at any moment. Generator-powered search works well for real-time data streams, such as log lines or network messages, because it lets you start processing immediately instead of waiting for all the data to arrive. It keeps memory usage low by holding only a small portion of the stream at any time, and it remains a sequential scan that is integrated with input and output operations for better responsiveness and scalability. The generator syntax makes this pattern easier to write and use, but each step in the iteration and each condition check still contributes to the overall cost of the search. Python code. Generator-powered search. This lesson demonstrates how generator-based search uses lazy evaluation and can stop early when it has found what it needs. By comparing generator search with a traditional list-based search on simple temperature readings, you can see how the generator processes only as many values as required. This approach avoids unnecessary work and keeps memory usage very small, since it does not store all results at once. Overall, generators provide a more efficient way to search through data when you do not need to examine every item. This line is simply a reminder that if the script needs any extra libraries beyond Python's standard ones, they should be installed using a package manager before running the code. It implies that the script mainly uses built-in Python features, so additional installations may not be necessary. Overall, it prompts you to check and prepare any required dependencies to ensure the program runs correctly. We begin with a list of temperature readings in Fahrenheit that includes a range of normal values and one extremely high, dangerous value. This list is meant to mimic real-world temperature data. Using it, we can demonstrate how to detect potentially hazardous temperatures. The key idea is to apply a generator-based approach to scan through the readings and identify those that represent dangerous heat levels. We define a function that checks whether a temperature in Fahrenheit is dangerously high. It takes a temperature value as input and returns true when the temperature is 100 degrees or higher. This signals that the temperature has reached a dangerous level. Because it returns a true or false result, this function serves as a predicate that can be used later to filter temperatures based on this condition. This description explains a generator function that processes a list of temperatures. It loops through each temperature, counting from 1, and announces which reading is being checked, along with its value in Fahrenheit. After printing this message, it yields the current temperature so the generator can pause and resume later. This behavior supports lazy evaluation and helps use memory more efficiently. We use a generator stream to produce Fahrenheit temperatures one at a time, instead of loading the entire list into memory. This means each temperature is only evaluated when needed, which is more efficient and supports lazy evaluation. By processing readings sequentially, we can easily examine each value in order. This is especially useful when we want to stop as soon as a certain condition is met, such as detecting a dangerously high temperature. We use the next function to scan the temperature stream and return the first value that meets the dangerous condition. Inside it, a generator checks each temperature with the dangerous temperature test and stops as soon as one qualifies, which shows early stopping. If no temperature is dangerous, next returns a default value of none. This method is efficient because it avoids unnecessary checks and takes advantage of the lazy evaluation of generators. The code searches for the first dangerous temperature and prints that result. It relies on a generator to scan through temperatures and stop as soon as one meets the dangerous condition. This early stopping avoids checking unnecessary values and reduces processing work. As a result, memory use stays low while still correctly identifying the first dangerous temperature. This script shows how a generator can efficiently search through a list of temperature readings. It works with Fahrenheit values that include a dangerously high temperature and checks each reading one at a time. Because the generator uses lazy evaluation, it only processes temperatures as they are needed. A generator expression finds the first reading that reaches the dangerous threshold and then stops immediately. This early stopping behavior illustrates how generators reduce unnecessary work and memory use, making them well-suited for large datasets. Abstraction versus control. High-level search features in Python, such as membership checks or library functions, let you focus on what you want to find instead of how to search for it. Rather than writing loops and conditions yourself, you state the goal, and Python performs the underlying search. This might be as simple as checking whether a user ID is in a collection, or as complex as retrieving the first matching record from a database. The detailed algorithms still run behind the scenes, but they are wrapped in a clearer, more readable interface. Python makes searching through data look simple, but it is important to understand what is happening underneath to write efficient programs. Different search choices, such as scanning through a list or using a hash-based lookup in a set or dictionary, rely on different algorithms. These approaches can have very different performance, especially as the amount of data grows. For small datasets, the difference may be minor, but in large applications, the search method you choose can determine whether your program stays fast or becomes slow. Balancing abstraction and control in Python is a deliberate design decision, not just a matter of style. In many cases, the most readable search methods are fast enough, and their clarity is more valuable than small performance gains from manual indexing. But when working with large datasets or complex web requests, it becomes important to understand the underlying algorithms. You should still favor high-level constructs, but know whether they rely on linear scans, tree structures, or hash lookups. This awareness lets you keep your code elegant while still meeting performance and reliability needs in demanding situations. Python code: abstraction versus control. This material focuses on the difference between using abstraction and direct control in simple search tasks. It contrasts checking whether a value is in a list using a built-in membership operation with manually searching through the list using a loop. By comparing these two approaches, you can see how abstraction hides low-level details while explicit looping exposes them. The goal is to observe how these choices affect both the clarity of the code and the performance of the search. The comment is reminding you that the script may depend on an external library that is not part of the standard tools. It serves as a placeholder, indicating that you might need to install additional packages for the code to work. This ensures that all required dependencies are available before you run the program. We begin by importing the time module so we can measure how long different parts of the code take to run. This module provides functions that let us record the moment when a block of code starts and when it finishes. By comparing these two times, we can calculate how long that operation took. This timing information is then used to compare the performance of different search methods in the script. We begin by creating a large list of user IDs for the system. This is done by generating numbers from 0 up to, but not including, 500,000, and converting that sequence into a list. The result is a large, easily accessible collection of user IDs. This simulated dataset is then used to perform operations such as searching and measuring performance later in the script. We intentionally choose a user ID that appears near the end of a long list so the search does not find it right away. By setting the target to 499,999, the search algorithms must scan almost the entire list. This setup lets us clearly observe how different search methods perform and compare the efficiency of abstract search techniques with more manual approaches. We begin by recording the current time with a high-precision performance counter to mark the start of our timing. Then, we check whether the target user ID is contained in the user list using a high-level membership test, which hides the internal search details. After this check finishes, we record the time again with the performance counter. By comparing the end time to the start time, we obtain the duration of the membership test operation. We measure how long a manual search takes by recording the time before and after the search. We start with a flag that says the target user has not been found, then loop through each user in the list. For each user, we check if it matches the target, and if it does, we set the flag to true and immediately stop the loop to avoid extra work. Comparing the start and end times gives us the total search duration, and this manual approach lets us control the process and stop as soon as the target is found. The code measures how long two different search methods take and converts those times from seconds to microseconds, so the results are easier to read. It finds the duration of the list membership test by subtracting the start time from the end time, then multiplying by 1 million. It does the same calculation for the manual loop search. Expressing both timings in microseconds makes it easier to compare the performance of the two approaches. This line checks whether both search methods successfully found the target user. It combines the result of the list membership test with the result of the manual loop search using a logical AND. If both results are true, it confirms that each method located the target. The outcome is then printed to the console to verify that the search operations worked correctly. This line of code reports how long the membership test using the list containment operator took to run. It uses the rounding function to express the time in microseconds with 2 decimal places so the result is easier to read. Presenting the timing this way makes it straightforward to compare the efficiency of using the in keyword with other approaches. The code measures how long a manual loop search takes and prints this time in microseconds. It rounds the measured value so the result is concise and easy to read. This makes it straightforward to compare the performance of manual searching with other search methods. We convert the list of users into a set so we can take advantage of the set's fast, hash-based lookup. This makes checking whether a specific user ID exists much quicker than scanning through a list. In other words, using a set improves the efficiency of membership tests compared to using a list. We start by recording the current time with a high-precision performance counter to mark the beginning of the set membership test. Then we check whether the target user ID is contained in the set of user IDs, using the set's hash-based lookup, which is typically faster than searching through a list. After this check, we record the time again to mark the end of the operation. Comparing the start and end times tells us how long the membership test took to run. The code measures how long a set membership test takes by subtracting the start time from the end time. It then converts this duration from seconds to microseconds by multiplying by 1 million. Using microseconds provides finer detail, making it easier to compare the performance of different search methods with greater precision. This code measures how long it takes to check whether a value is in a set, which uses a different and more efficient algorithm than lists for membership tests. It then prints the time in microseconds, rounded to 2 decimal places. This highlights how fast set membership checks can be compared to other data structures. This script compares 3 ways to search for a user ID in a large collection and shows the trade-off between abstraction and control. It first uses Python's built-in list membership check, which is a high-level, optimized approach, and then repeats the search with a manual loop that gives more control but is slower. Finally, it uses a set for the membership test, which relies on hash-based lookups and is significantly faster than both list methods. The measured times, reported in microseconds, show that the set search is fastest, followed by the built-in list check, with the manual loop being the slowest. In this lecture, you learned to use Python's built-in search capabilities effectively for common tasks. Apply the bisect module to maintain sorted sequences efficiently. And relate high-level Python search constructs to their underlying algorithmic behavior. In the next module, Module 5, we will go over sorting algorithms.
Thank you for your attention. See you all in the next lecture.